Hi, I'd like to present our research work, CHIMERA, Fuzzing P4 network infrastructure for multi-plane bug detection and vulnerability discovery. I'm Jiwon Kim from Purdue University, and this work has been collaborated with Georgetown University. Before introducing P4 infrastructure, let me first introduce software-defined networking. Software-defined networking evolved from traditional networking, which relied on bulky, hardware-intensive routers. Such complex network devices have both data plane forwarding and control plane logics. Therefore, to determine the path among devices, they must communicate control plane messages between them. Instead, software-defined networking decouples the control plane into a remote controller, which manages forwarding devices through the OpenFlow protocol. Then the data plane handles packets with flow rules installed by the remote controller. However, OpenFlow is a fixed set of messages based on TCP/IP. If the network developers want to implement customized networking beyond RFC's documents, they need to extend not only the OpenFlow specification, but also the data plane functionality. Therefore, the network community has developed the P4 language. P4 is a domain-specific language to define how packets are processed. With P4, network developers can write a P4 program to implement their own network features. The P4 program will be compiled into two outputs, one for a protocol between the controller and the data plane device, and the other for an executable that can be run on the programmable data plane switch. Let me briefly explain how the P4 program works. The P4 program receives an input packet, and based on table entries, the program will drop or forward the packet as an output. Accordingly, the P4 architecture needs to implement this P4 program correctly. Applications will install table entries through a controller to the switch. The hosts connected to the programmable switch will send the input packet and receive the output packet. Since the P4 program defines how packets are processed at a high level, the behavior of the P4 infrastructure and the P4 program should be identical. However, there could be software bugs within the P4 infrastructure, either controller or switch. In this case, the behavior of P4 infrastructure can differ from that of the P4 program. Therefore, the P4 program can serve as a criterion to detect P4 infrastructure bugs. Moreover, P4 infrastructure consists of a complex programmable networking stack. For example, the switch includes at least 3 layers. From the bottom to the top, there could be a device implementation, a switch operating system, and a server to receive P4 protocol messages. In the controller, there could be a P4 protocol client, a P4 driver, a core layer to manage P4 entities like flow rules, and a P4 translator to support P4 agnostic applications. You don't have to understand each detail of the layers, but please consider P4 infrastructure can be composed of such complex layers. And any software layer can be buggy. To better understand the bug reports on the complex stack, we selected 5 open source projects for each layer. Then we analyzed bug reports based on bug triggers. As a result, 83.3% of bugs are triggered by control plane inputs. Additionally, a non-negligible 20.8% of bugs are caused by multi-plane inputs simultaneously. Therefore, to trigger more bugs, a P4 testing tool needs to provide multi-plane inputs at the same time. Until now, I have shared the background of P4 infrastructure bugs. Let's move on to our objective, fuzzing P4 infrastructure. A fuzzer basically gives random inputs to the target program. It will detect crashes or semantic bugs. Then it can track the covered paths of the program, which will provide feedback for the tool. There have been existing fuzzing tools that can be run to test the P4 environment. However, there are several limitations. Let me tackle random inputs first. There are two categories of SDN fuzzing tools: data plane fuzzers and control plane fuzzers. Data plane fuzzers mutate data plane packets, but use a fixed set of control plane rules, such as FP4. Control plane fuzzers mutate control plane messages, such as flow rules, but they only generate special data plane traffic, like packet flooding or a representative packet to test connectivity, like intender. Therefore, existing single plane SDN fuzzers only mutate single plane inputs like packets or control plane messages. We've discussed one limitation of SDN fuzzers, which utilize single plane input mutation. Let's tackle with the bug oracle. Existing P4 fuzzing tools rely on manual validation, such as AP4 and P6. With these tools, testers, like users, have to extend the target P4 program with queries or assertions. Then, the testers will execute this P4 program, provide random inputs, and be able to detect bugs when the assertion fails. However, it requires non-trivial manual effort. Additionally, such an oracle might be incomplete and prone to user errors. In short, existing fuzzing tools for SDN or P4 infrastructure only mutate single plane inputs and rely on manual oracles. However, as I showed earlier, we found two takeaways. First, to find more bugs, a P4 fuzzer needs multi-plane inputs. Second, the P4 program can be a criterion for P4 infrastructure bugs. Therefore, we developed CHIMERA to fuzz P4 infrastructure effectively. First, we support multi-plane testing with smart mutators for both data plane packets and control plane rules. In addition, we utilize P4 concurrent execution as our bug oracle instead of a manual validation. Let's explore each of them in detail. First, CHIMERA can support multi-plane inputs. However, we should consider interdependencies between these inputs, input packet, and table entry. The P4 program consists of three stages. First, the parser determines which packet header is of interest. The match action pipeline defines how to handle packets. The parser has a queuing policy. Given this P4 program, a P4 fuzzer can give a random packet with a random protocol number like 255 and random payload. However, the random packet will be easily dropped by this P4 program because it doesn't align with the P4 parser with TCP and UDP. Also, as shown in the table entry on the upper right of the slide, the tool can provide a random value for the IPv4 source address like 8.8.8.8 or a random string for the match field name in match 2. However, these random strings will not align with the P4 pipeline definition as well as the input packet. To consider such interdependencies, we developed smart mutators for P4 program. Instead of randomly generating packets, we refer to the P4 program directly. CHIMERA randomly chose a parser path like UDP and INT, which is in-band network telemetry. Then CHIMERA can reversely generate valid packet header values like IPv4 protocol number as 17 for UDP. We call it parser-aware packet mutation. For the table entry, we refer not only to the P4 program definition, but also to the given input packet headers. Therefore, we can guarantee that generated table entries are valid with proper values for specific match fields and string match names. We call it header-guided rule generation. Second, there have been existing approaches in bug discovery on P4. In addition to manual oracle like P4 fuzzers, there are test oracles built upon a P4 symbolic execution tool. These tools collect the path conditions of the P4 program, use the J3 solver to find input variables that satisfy these conditions and generate test cases, including an input packet, table entries, and an output packet. However, since test oracle are not designed for fuzzing, this approach doesn't scale well. Instead, we implemented a P4 concurrent execution, P4CE. By reading an input packet and table entries, P4CE can execute each statement in P4 with these given values, then calculate an expected output packet. By comparing this output value with the actual behavior of the P4 infrastructure, we can detect discrepancies between them. At a high level, the P4 program should be identical to the P4 infrastructure, allowing us to detect such discrepancies as bugs. We evaluated CHIMERA in the open source P4 PIP infrastructure, and we found 7 new bugs in total with 2 CVEs assigned. Among them, 2 bugs are triggered by multi-plane inputs simultaneously, and 5 bugs are detected only by P4CE. 2 CVEs can enable network-wide denial of service attacks and tampering with host information in the controller. We compared CHIMERA to 2 existing fuzzers, FP4 for the data plane fuzzer and Intender for the control plane fuzzer. As a result, CHIMERA can get the highest coverage in both the data plane and the control plane. Also, CHIMERA can achieve up to 3.5 times higher bug detection rate. In this slide, I'd like to present a case study involving a newly discovered CVE. This CVE can allow the attacker to exploit the denial of service attack on the ONOS controller. Host A, the malicious attacker, can flood invalid IPv4 packets. But due to the rule 1, which sends packets from host A IPv4 address to the controller, these packets will be delivered to the controller. However, at ONOS core, it starts showing error messages saying unable to interpret inbound packet due to invalid IPv4 packets sent by host A. Since the programmable switch can handle invalid IPv4 packets with high performance, the controller core prints error messages continuously without delivering such packets to the applications, which causes denial of service in the controller. CHIMERA can discover this vulnerability efficiently. Since CHIMERA supports multi-plane testing, it can detect this bug where the data plane behavior affects the controller's core logic, which is cross-plane bug. Parser over packet mutation, PAPM, can guarantee that packets are specific to a P4 program like IPv4 header. Header-guided rule generation can generate valid rules that match packets such as a host A address as the IPv4 source and a valid action name like send to CPU. Lastly, P4CE, the P4 concurrent execution, can detect the erroneous behavior of P4 infrastructure, which is different from that of the P4 program. The P4 program expects this input packet to be delivered to the controller and applications correctly. However, due to the error messages in the core, the applications cannot receive the packet. To conclude, we investigated 41 bug reports in 5 open source projects. We designed CHIMERA with new fuzzing techniques for P4 infrastructure. We developed P4 concurrent execution as a bug oracle. We developed smart mutators like parser-aware packet mutation and header-guided rule generation. In total, we can discover 7 new bugs and 2 CVs assigned for the P4 infrastructure. Thank you for listening to my talk.